Okay, where were we? So we were looking to decompose, want to understand the decomposition, and maybe I'll write more than usual. I say that as the writing gets worse and worse. Want to understand the decomposition of L2. This is really, come on.
I mean, is this like the thing where you have to like reset the tablet or something? Or
it's correctly showing the location of the pen. It's just not correctly doing what the pen, like just now I made a loop and it made a straight line. So I think it's struggling with this between Zoom and the pen and the, it's okay. We'll make do. I'll write slower. L2 of G mod gamma with respect to Haar measure. G for us is GL1 of the Adels, also known as the Edels. Gamma is the discrete subgroup GL1Q. Am I writing big enough? How big is this coming through on your computers?
it's okay. Good on my end.
Okay. Too big?
Can't fit much on a page.
That's true, but I can zoom out and show more of the page. Okay, we'll get through this little at a time. Okay, we want to understand the decomposition of L2 into irreducibles. In this special case, G is abelian. So we will have one-dimensional irreducibles, one-dimensional irreducible representations, let's say
So like
W.
Right.
What's that?
So like in a similar way to it's going to be like in a similar way to the R case where it's like you don't actually have L2 functions.
That's right. That's right. So this won't be an L2 function. That's true. This won't be an L2 function, but it'll be almost L2.
Okay.
Okay. So phi is a function. So phi is this is really going to get annoying. Phi is a map, well, from G to C, but it's really a map from G mod gamma to C, i.e. for all G in G. I remind you that this is just Edels. And for all gamma in gamma, gamma is the multiplicative rationals. Phi of gamma G is just equal to phi of gamma. Okay, so that's the automorphy. So these irreducibles, these are called automorphic representations. So this space is what we will call automorphic. Automorphic, in other words, G invariant irreducible representation, subspaces, automorphic representation.
This is sort of similar how to like exponentials are periodic, right?
Exactly. Exactly. The exponential function is exactly an instance of this with the reals modulo the integers. Exactly right. This is supposed to be a parenthesis. Although it does work if I put a gamma G here to show that phi, some people do write this as phi is a function on gamma cosets.
Right.
So, all right. Okay. And so this is just the automorphy. This is the fact that we're decomposing functions that are invariant under gamma, but we also want it to be an irreducible representation. What does that mean? And phi is irreducible. So that means that pi G acting on phi, this is a new function. So what value does it take at a point H? It's the right regular representation. This is the right regular representation. Well, restricted to this irreducible subspace. I mean, the right regular representation acts on all of L2G. we're already thinking about the gamma invariant, the automorphic subspace, and now we're decomposing that even further into these irreducibles. But the representation still does the same thing to functions. What does it do to the function phi? It takes phi, instead of evaluating at h, it evaluates it at, I really have to move very slowly, hg. Okay, and the fact that this is just some constant multiple of itself. That's what it means to be irreducible. So this is some constant multiple. I don't know what that constant is. Let's say omega. Some constant multiple that depends on g. You'll have different constants depending on g. Times phi itself. In other words, the value of phi at h.
And more than irreducibles because it's one-dimensional, right?
Exactly. Exactly. So maybe I'll already point out that this is very special to abelian.
Right.
Not true in general. How slow do I have to go? Not true. This is just awful. In general. No more snow days. In general. So already for GL2, GL2 Adels of Q. The irreducible representations will be not abelian and hence not one-dimensional. They won't even be finite dimensional. They'll all be infinite dimensional.
So how do you make do with this? You know, like how do you overcome that?
We're going to discuss that. Yeah. I might again gloss over some of the functional analysis that goes into making things rigorous, but I'll explain to you how you work with these things in practice. And it's actually very simple.
And they're all infinite dimensional.
Except for the trivial. The trivial representation is always a one-dimensional space. When this quotient has finite volume, when G mod gamma has finite volume, you always have a trivial representation. Okay. Good. So this is just an aside. Okay. So what is this? What is this omega? So this omega, and this is actually something general. So the center will always act by some character. We'll come back to that. So omega here is what's called a Hecke character. Hecke character. Come on. Is this as painful for you as it is for me?
It's pretty painful.
A Hecke character. So it's a
Really
character.
painful, yes.
Very painful. Sorry. It's a character from the Edels modulo the rationals to C. Don't know what to do. I don't know how to make this better. We'll just push right ahead. So it's a character. So well, let's stare at these two things side by side. These two facts right here, side by side. Okay, so these two facts side by side tell us what? Well, let me plug in H is gamma. So phi of gamma G on one hand can be interpreted as pi G. Jesus, come on.
It'd be worth at least like removing the tablet and putting it back in, or
No, it's just the speed of my computer. My computer is having a lot of trouble
mm,
handling all of this Zoom and Notability at the same time.
Is it on the charger right now?
It's charging. It's charging. Yeah, sorry. We'll do the best we can. I don't know what else we can do. On one hand, this G, because it's H times G, so this is pi G. On the other hand, this is phi of G, because phi is invariant. Now, what we just said is that pi G acting on phi is just some character, omega G, times the value of phi. But phi is, again, gamma invariant. So what's phi of gamma the same as? Yeah, it's just phi of the identity, exactly. This is just some constant. In other words, the one-dimensional automorphic representations, where in the case of GL1, the automorphic representations are just Hecke characters. Just some constant multiple times a Hecke character.
so it's like you have these representations for G, but really like this constant has a lot of properties, right? Like
That's right.
Right.
So let's try to understand what we can say about this WG. So this W is a character. W is a global character. It's a character on all of the, it's a global character. Never writing the word character again. Takes way too long. In other words, it's on the whole Adels or Edels. But in fact, notice that because it's a character, in other words, so what does it mean to be a character? It's the W of G1, G2 is W omega whatever of G1 times omega of G2. By the way, pi is unitary, right? Pi, this representation pi is a unitary representation. So what do we know about all the values of omega? Right, it's unitary, meaning the inner product, if I move some phi1 and
equal to
phi2,
0,
close. If I move some phi1 and some phi2 by pi, by the same element G. So now I have two new, I used to have phi1 was over here somewhere, phi2 was over here somewhere. I move both of them. What's the inner product? The integral against the L2 space, against Harmeasure. Well, unitary means that the inner product.
I mean, you can get rid of the pi's, right?
Exactly. It doesn't change the inner product. And so if you think about what that means for the value of omega, well, if this pops out an omega, this pops out an omega bar. So this pops out an omega absolute value squared. So this takes absolute values, not just in the complex numbers, but in the unit circle, inside the complex numbers.
I see.
Okay. Okay, so it's a global character, but I claim by this property, it's actually a product of local characters. So we're going to let omega sub p, or nu, if we want to think about it even more generally than just for the primes, let omega sub p of GP be the value of omega on the number. So remember, what's G? G is an edel, so it's G infinity, G2, G3.
And then eventually
dot.
all of these are in ZP cross, right?
Exactly, and almost all of the GPs are in ZP cross. Are in ZP cross. Okay, so what am I going to do? How do I make a function that just takes values in the p-adic numbers? I'm going to put 1 at gamma infinity, 1 at gamma 2, and so on. When I get to gamma p, when I get to the pth place, I'll put GP. And then I'll put 1s everywhere else.
Wait, but what are we trying to do here?
So this defines, this gives a character. This is a character on QP cross. So this WP is a map from QP cross to, well, the unit circle inside the complex plane. And it's a character.
Oh, I see. Okay.
It's a character because all I'm doing is restricting omega to the pth place. It's a character on all of the adels. It takes the same values on rational, non-zero rational multiples. And so check this out. That means we can take omega of G and write it as a product over all p's less than or equal to infinity of omega p of GP. Is this clear? This is simply because if you take gamma infinity 1, 1, and so on times 1 gamma 2 G2 1, 1 times, okay, you see what I'm doing, 1, 1 G3 and all ones.
Right. So you could just have this as an input for W and then just factor it out.
That's exactly it. Because it's a multiple, because it's a character, it has this multiplicative structure, but the edel group has this multiplicative structure. As long as almost every GP is in ZP cross, then this will exactly come out to G infinity, G2, G3, and so on.
So you won't end up with any convergence issues or anything.
Right, because we're in ZP cross. So let's talk about that, in fact. So because this character came from, it's the character of a continuous representation. So this regular representation, there's two things about it. One of it is unitary, two is it's continuous. So the pre-image, so this omega is continuous. It's continuous on all the adels, but it's in particular if I restrict to the finite adels. The finite adels are just the ones without R in it. So this is just the product over P strictly less than infinity of QP cross with the restriction that almost all places you're in ZP cross. Okay, so that the edels themselves, the edels are the reals, the multiplicative reals cross the finite edels.
This allows you, you're saying, to use multiplicativity a countable number of times, right?
That's
So,
right.
like,
So these are, let me just put here finite edels, the finite edels. Maybe sometimes I go too fast. I don't think I'm going too fast for anybody today, unfortunately. Or fortunately. So it's continuous on this, which means that now this is a totally disconnected space. This is totally disconnected. And there's a nice exercise. Ooh, speaking of exercises, I'll put some more exercises. Oh, did we say Friday, right? Friday would have some exercises due. This is a totally disconnected space. This, come on. This is so painful. Technology is amazing when it works. And when it just barely doesn't work, that's the worst. If this didn't work at all, I would just say forget it. You know, we'll just skip and I'll give you another one. But it works close enough to being manageable. Okay. This is a totally disconnected space. So if you look at the kernel, so if you look at the pre-image of the identity, right, the kernel as a map into the complex numbers, these are the complex numbers. Jesus. It's like a first grader is writing these things. So the pre-image of one of the, in other words, the kernel, let's just write the kernel, you know what the kernel is. The kernel, what is it? Well, it has to be some nice open set in this topology. And so it contains what's an open set? It's a product of some open sets UP for some finite set of places P. Times the places not in P of ZP cross. Okay, i.e. for almost every place P, this WP, this local character, this WP, if restricted to ZP cross, will take the value exactly 1, will be identically 1 on ZP cross. Right, that's what it means to be in the kernel. The kernel is that you map to 1. 1 is the identity element. Emily, does that make sense? Do you have a question? No, okay. So these are the ones that are called unramified. So definition, I guess I'll put it here. Definition. This local character omega P is unramified
I'm like, I guess I'm a little confused about
yes
why, Right, because you're taking this W is mapping to the circle, right?
Yes,
And so if I take some element, so you're saying that this kernel contains open sets that look like this,
yes,
and okay, so this, okay, so for the circle, you're saying, right, the identity element's just one, right? Because it's a multiplicative group.
yeah. The kernel, the kernel is what's the thing that maps to the identity.
Right.
And so if you look at the finite Edels, this is a totally disconnected space, and it's a continuous action. So the kernel has to contain some open. And the basis for the opens is sets of this form.
Oh, okay. I see. So you're just saying, it might be this open set, but that's good enough to say what you have in the bottom.
That's right. Right. So the fact that the kernel contains the product of almost all ZPs means when you restrict almost all of these local characters to ZP cross, it only takes the value 1. So that's what it means to be unramified. Okay.
And I also wanted to ask or say, right, that this Hecke stuff you're saying is really behaving very, very similarly to the modular form stuff, right?
Yes. In GL2, one of the possible irreducible representations will exactly be a space spanned by modular forms.
Interesting. Yeah, because I mean, you're using the unitary stuff and all this multiplicativity is the same arguments they go through for modular forms, right? So
exactly right. So there'll be modular forms which are non-spherical irreducible representations, or they're sort of the lowest weight. Okay, we're going to get to raising and lowering operators and weights of modular forms, and this is all to come. Not at this rate, so we're back in person but it is all to come. So let's just look at this for a second. We have a local character. It's unramified. What does that mean? If we have an some of these characters will be ramified. I mean, there's no reason to be everywhere unramified. What does it mean to be ramified? So if omega p, if this local character is unramified,
or is ramified?
Nope.
All right.
I've lost my pen. Okay. Okay, if it's unramified, oh, that's much better. Right? You can see that?
Yeah.
Okay, if it's unramified, then what do we know about omega of any number? So, and if G, let's say GP, is in QP cross, well, if it's in QP cross, then it's equal to some, right? What is QP cross? It's been a minute since we've done this stuff. Hopefully you guys remember it. That means GP looks like some a minus n p to the minus n plus it has some expansion a minus 1 p to the minus 1 plus some a0 plus some a1 p a2 p squared, and now we have
not
an infinite
identically
sequence.
zero.
Sorry?
And not identically zero.
And it's not identically zero. Exactly. That's the only thing. Every p-adic rational is invertible except 0 itself. Okay. So it's equal to, so this is the least non-zero entry. So it's equal to p to some power, p to the m. I guess here I have negative n, but I don't know. It might be positive, it might be negative. Times an element. So it's in p to the m times something in ZP cross. Right? Every invertible p-adic rational is in some ZP cross shifted by either up or down by some power of p. And so what do we know about omega of p? Omega p of g. GP.
And this is a character, right?
Well, it's a character, so it's multiplicative. And so this is any GP is P to the M times an element U in ZP cross.
Right, but you just said restricted to that, it's one, right?
If but restricted to that, it's one. So this and this is multiplicative. So this is omega P of P to the M, which I can pull out. M is an integer, times omega P of U, which is one. So it's completely determined. So unramified characters, unramified, then omega P is completely determined by the value of omega P of P.
And so, like, when you say unramified and ramified, how is this related to that concept in like number fields?
Oh, I thought you were going to say, how is this related to Dirichlet characters? Because it's that's where we're headed. Number fields, it's the same idea, except now you have to take the integers inside the. So you have your number field, you have your field extension, your global field K, and now you have your place, your prime ideal P, and you have your localization K sub P, and then you have the ring of integers of that localization O sub P and O sub P cross, the invertible, the units in that ring. And so being unramified is that you're the identity on that group of units. It's exactly the same thing. Just replace ZP by O. O is usually the symbol for the ring of integers.
Because I thought of the ramified stuff as, the primes that split versus the ones that don't, but I guess this is the equivalent.
It's not unrelated, in fact. It's not unrelated, and maybe I'll have a chance, maybe not today, but maybe next time I'll show you why that language is carries over appropriately. What's ramified and what isn't. Okay. So that's what we know about the unramified characters.
And how are these related to the Dirichlet characters?
Yes. So what do we know about where are we? Here, right. So the kernel, so we know that we have some open set. We have some otherwise open set at the other places. If omega P is ramified, well, what does that mean? That means that there exists some unit U in ZP cross for which omega P of U is not exactly one, is not identically one. Okay, so if we're looking at the kernel, then the kernel of omega P, what gets mapped to one? All of ZP cross does not get mapped to one because there's an element that didn't get mapped to one.
I mean, you wrote it up there, right? You named it.
Well, I named it UP.
Yeah.
I named it UP, but I want to see it more precisely. So what is it? Certainly one gets mapped to one. It's a character. So one is the element with a one plus nothing. Well, let me write a typical element of A1P plus A2P squared plus A3P cubed, and so on, right? So one is certainly in the kernel. Omega P of one is one. If it's a character, that had better be the case. Okay, so I know that I can't take all of ZP and pull it into the kernel. There's something not in the kernel. But I also know that there's an open set around one that is in the kernel. So the question is, what's the largest? So this contains 1 plus P to some power, M, I guess. No
and again, here you're using this, that you're using that this is continuous and like completely disconnected.
Right, exactly.
For this, to say that there's open ball around one, given that
exactly
one is
right.
in the kernel.
Exactly right.
Okay.
Okay, so the open ball is going to be 1 plus some ZP, So some of these I might have to, so I check, is it true that regardless of the value of A1, I wind up in the kernel? If not, then I go to A2. If not, then I go to A3. But at some point, one of these sets is going to be in the kernel. So we're with M maximal, with M, not maximal, minimal.
Right.
Minimal. So what's the largest set of this form that's contained in the kernel? There's going to be such, because I can't take M equals 0. M equals 0 would be that all of ZP, in particular all of ZP cross, but with M minimal, and M is at least 1. And we say that P to the M is the conductor, is the local conductor of omega P.
Huh.
Okay, maybe I should
Maybe
call
a
it
character.
with M minimal, so we'll call that M sub P.
Character mods P to the M.
Well, let's see. So what do we know? So this is some character. We know it's the identity on once you go out to A M P to the M, its identity on all sets of this form. If I make all of these A's equal to 0, but I don't know what it does on all of the other A's, and I don't know what it does on all of ZP. Of course, if I know what it does on all of ZP, then I know what it does everywhere because of this. Except it won't be 1, it'll just be the value on ZP. And so the question is, so note, observe that this 1 plus M P to the M ZP is a multiplicative subgroup of ZP cross. Is that true? If I take two elements of this form with a 1, a bunch of zeros, and then something P to the M, and I multiply them together, does it start with a 1? Does it have nothing between P and P to the M minus 1, and then has whatever after that?
And so will its inverse?
And so it's inverse. Yes, it's inverse. If you try to invert an element like this, it's also of the form 1 plus a bunch of zeros, and then A bar, AM bar, and then you have to carry the rest of the digits out. So that's a multiplicative subgroup. So what is the quotient? Look at the quotient. If I take ZP cross mod this group 1 plus P to the M ZP. So what's a nice set of representatives for any element of ZP cross modded out by, if I can multiply by 1 plus whatever after the pth place. I claim that a set of representatives for this is A0 not equal to 0 plus A1P plus up to A M minus 1 P to the M minus 1.
Yeah, that does make sense.
Right? ZP cross is you can have any digits. And now this is saying, okay, but I can change the last digits to be whatever I want. In particular, I can make them, all zeros if I like. But what is this space isomorphic to?
I mean, Z mod P to the MZ. Yeah.
Except
Yeah.
the first digit can't be a multiple of P. It's got to be coprime to P.
Right. So,
But that means that the local characters are characters on Z mod P to the M Z. But we know what the characters on Z mod P to the M Z are.
yeah, Dirichlet ones.
They're Dirichlet characters. They're Dirichlet characters. So whatever omega p is doing, omega p restricted to ZP, restricted to ZP cross, is just, so there exists a Dirichlet character, let's call this chi sub p to the n, p to the m, p to the m, the m depends on p, of course, such that when you restrict omega p to this, it's just chi of p to the mp at that number, at that finite number.
And like the character like literally filters through these isomorphisms. Like,
Well, because omega is a character. Omega is itself a multiplicative group, and so now a multiplicative character. And so what are the multiplicative, by definition, the Dirichlet characters are the multiplicative characters on these finite groups.
I see. So it's like isomorphism, just saying like it behaves precisely like that. So
Yes.
in any ways you're mapping to the circle, right? And so do these. So
Yes.
it actually makes sense to say it's literally equal.
Well, in the sense that when I take an element, so if I take i.e. omega p of some a0 plus a1p plus an infinite sequence, this is an element of QP. So it's an infinite sequence. In fact, it's an element of ZP cross.
Right.
It's equal to chi of p to the mp evaluated at a finite integer, which is a0 plus a1p up to a m minus 1 p to the m minus 1.
Yeah, it's this truncation. Yeah, we should have had before.
Where this is in z mod p to the mz.
This is crazy.
Okay. So what have we learned? This is true at every place. Finitely many of the places are ramified.
So you have a product of characters or something?
So there's a Dirichlet character. So to put it all together, put them all together. Let capital N be the product over the ramified primes of p to the mp. Then let chi mod n be the product of these chi p to the mps.
And since they're relatively prime.
Yep. I'm using the fact that z mod n cross is the product over the primes.
Yeah.
Z mod p to the m.
This is Chinese remainder theorem.
This is
really.
the Chinese remainder theorem. Okay. So there's a single character so that omega p, such that omega p, such that omega, the whole thing omega, well, how do I want to say this? Restricted
to
yeah, restricted to the finite Adels, and in fact restricted to the product of ZP crosses, restricted to the product of all the ZP crosses, evaluates to chi. Okay, and once you know what it does on all the units, you know what it does everywhere, because i.e., should I spell this out more in more detail, or it's sort of one of these things that the more detail you give, the it just becomes notation after a while, as opposed to ideas. So hopefully the ideas are clear. So we've constructed, let's do this again. We can go from a Dirichlet character, from a character chi mod n. We can construct a Hecke character omega, on the edels. It'll be invariant under left multiplication, although it doesn't matter, by the multiplicative rationals. How? So what value do we take? So omega will be the product over local omegas of GPs. And the local omegas are determined how? I'm just summarizing, so summary. What we did above is the other direction. From omega, we got to the local omegas. From the local omegas, almost everywhere we just had trivial characters, but then at the ramified places, we had some characters. We could put those characters together and make a character mod n.
Maybe
Let's go in the other direction. From a character mod n, we can construct a Hecke character,
right, so
that this is a complete bijection. And by the way, these will all be primitive. This character will be primitive. A primitive character. So we have a 1-to-1 from a primitive character.
How do we know that it's going to be primitive?
Yeah, so if it's not primitive, then this m that you took here wasn't the minimal one.
So it comes from there.
Yeah, it's an easy exercise that if it came from some divisor, well, the only way you could do that is by taking some non-minimal choice of conductor.
Right. Because you could have just taken some, like, big enough power, right? And
That's right. But I took the minimal power, so that determines the conductor exactly. And what is if omega p is unramified, or equivalently, p does not divide n.
right, I mean, just set those places to be 1, right?
Yes, exactly. Of p to the mu. So any element of G is of the form p to the mu. This is chi of p to the m. That's it. It's just chi of p to the m. Right? It's just determined by the value of omega p at p. That can be whatever it is. I mean, this character is a function mod n that we can extend to a function on the integers. And so it gives some value to p. That just depends on the residue class of p mod capital N.
Huh. So even for the unramified places, you're still using this chi,
That's right.
and nothing breaks.
It can't. I mean, this is what happened above. That's to okay. So that is to make it invariant under the. We have to be able to put all of these together, so that if you're in Q cross, this thing needs to be 1. So omega restricted to Q cross needs to be identically 1. That's exactly what this invariance means. Okay, and if omega is ramified, if omega p is ramified with conductor p to the m, then omega p of p to the m times a unit is again is the value of the character on the unit when you think of the unit restricted to this. So you, in other words, if you, I mean, I wrote it up here. We could say the image of u in the mod p to the m, if you like, u mod p to the m.
Wait, again, how do we deal with the real place again?
Okay, and then let's talk about the real place. We haven't talked about the real place yet. We need to do one more thing. For p equals infinity, at the real place, what do we do? What are the real characters? In fact, it's an exercise. So maybe I'll say exercise. The only unitary characters on the reals are taking absolute value and raising it to some power. And if it's unitary, that power has to be purely imaginary. because it has to have absolute value 1. Right? What's a multiplicative function on the continuous reals? On the multiplicative reals, invertible reals. And there's one other thing you can do. You can either do nothing, or you can multiply by the sign. In other words, this is a number in R cross.
Right.
So it's signed, it's either positive or negative. And you can just take the absolute value, or you can take the absolute value times sign. And that's still, sign is also a character.
Because you have to map to the circle, right? That's sort of the.
You have to map to the circle. Yeah, sign is plus or minus 1. It's +1 if you're positive, it's -1 if you're negative.
Right.
Both of these are characters. This character comes from the disconnectedness of R cross. This character is just the, the character on the reals, on the positive reals. And these are the two characters. And in fact, for consistency, what you should do is you should assign the character, you should assign omega infinity 1 if chi of -1 is 1, if the character is even. Otherwise, if the character is odd, then you assign it, then you give it, then you multiply by this sign.
It's just what, make things be cleaner, or?
No, so that it's invariant, so that it's restriction to, this makes it so that omega of -1 multiplies out exactly correctly to be 1 on the rationals. Yeah, of course, I'm rushing this because I wasted the first bit of the lecture. What can I do?
And like, how did Tate know these things were going to happen when he was building this theory?
Oh, did he know before he started how it was
Like,
going to work out?
Was he designing the theory so that exactly this would happen, or was this just like a nice coincidence of the things he was looking at?
He was not, I think, looking at things. So he was, okay. He was definitely thinking about Hecke characters. He was giving a new viewpoint on Hecke characters and recovering this whole theory of Hecke characters. He was not, it's much later that people realized that what he was doing was GL1 and automorphic representations on GL1. It's a trivial realization, but until you worry about GL2, you don't think of the edels as GL1.
And there's no point, right?
In that sense, he was ahead of his time. All right. With the 10 minutes left, I think we can just go over what you do with these new characters. So given these, given such an automorphic representation, Adelic automorphic representation, phi, by which I mean omega, by which I just mean the Dirichlet character chi, since everything is this very fancy thing built on top of a very simple object. Let's attach an L function. Attach an L function to phi, which of course should be the L function of chi. I think we can do it in 10 minutes because it's something we've done again and again and again. Okay, is everybody with me? Does anybody have any questions? Nick, you have a question, or you just no?
Nope, I'm good.
Okay. So what are we going to do? Remember what we did before. We had a function. So we took a test function to make zeta. To make zeta, we took a test function, a test vector, f in the Schwartz space of the Adels. We made a theta function out of it, theta f, at t. T was an edel. That was by summing over the q in the rationals, f of q times t. You guys remember this? This was a little while ago, so let's dust off our caps. This sum over the rationals secretly is a sum just over the the denominators are fixed. So secretly, this is just a regular old Poisson summation formula. And then what we did is we took the Mellin transform. Then we looked at the Mellin transform at t, which was an integral over, this is a function, this theta function is a function on E dels that's invariant under the multiplicative rationals. So we took this quotient space, we took the theta function at t, and we multiplied it by a character, t to the I, well, t to the s, this Adelic character with multiplicative Haar measure on the E dels. And this came out to, after a little calculation, this came out to something like the Mellin transform of f infinity times zeta. At least if f was everywhere unrounded, if all of the fp's are the indicator functions of zp's, and not just almost all. That sound familiar?
Because that was how we were dealing with our test function, right?
Right. Right. The being Schwartz means that almost every place is the indicator function of zp.
So is what you're saying, you can change you can make your test function a bit more flexible, and then you might get other things? Or?
If you make it more flexible, then you won't get, so this zp we got as an Euler product over all primes of 1 minus 1 over p to the s inverse. And if we if we make our test function more flexible, well, we'll get some potentially other factors at finitely many places, but at all but finitely many places we'll have exactly this Euler factor. Okay, and this was all if the real part of s is large enough. So what are we going to do? Instead of putting just a character at infinity, so now, instead of just integrating over the E dels of our theta function of our Schwartz function,
You can like twist it.
I want to put a character here. I want to put omega of t. We can put still a t to the s, d cross t.
Is omega also, you're also including the real place for that?
I'm also including the real
omega
place
as well. Okay.
That's right. That's right. Bless you. Okay. So as before, should we redo how we unfold, or you guys remember how unfolding works? If we have an integral over the Adels mod the rationals, and this is a sum on the rationals. Oh, I want to take away the value at 0. In fact, I want to take away the value at 0, as usual for a theta function. I don't take the constant term. I can't integrate the constant term. Okay, we have an integral on a star mod q star, and then a sum over q star. So when we unfold, we just get an integral over all of the E dels, and then little f of t, omega of t, and then t to the s.
Right, after expanding out and reorganizing and whatnot.
Yep. Okay. But now this factors, f is multiplicative, where it's a finite linear combination of multiplicative things. So let's just take it to be multiplicative. Let's take it to factor. So it's a product over p's, an integral over qp crosses of the local f at the local p, the local character at the local t, the local valuation of the local t to the complex number s, and then the local Haar measure, multiplicative Haar measure. Remember, this is normalized. The normalization.
It's like 1 over p minus 1 or something.
Yeah, there's a constant that we have to put, or we can just remember that the integral of zp cross of 1 p star p is 1. Exactly. That's how we made that normalization. Okay. Let's look at p. This is almost all p are like this. This is the generic p. with Fp being the indicator function of Zp and omega p being unramified. Okay, almost every place looks like this. So what do we get for the integral over QP cross Fp omega p?
Wait,
Yeah,
you're saying that for almost all P, both of these things are true,
that's right.
right? But the
There's a
list
set of
might
places
be,
where either of them fails is finite. So their
Right,
union
right,
is
right.
finite.
exactly.
Okay. Fp is the indicator function of Zp. So this integral is actually an integral just over Zp take away 0. The only element of QP that's cross that's not in Zp is 0. Then I have this omega p. And remember, this integral, the Zp take away 0 is a sum over positive integers n of the integral over p to the n Zp cross. Every non-zero Adelic p-adic integer has some non-zero leading term, and then
It's just that union formula you talked
just
about
the
a
union
long
formula,
time ago.
exactly. Okay, so then I have omega p of Tp. The norm on this thing is exactly p to the minus n. So I get p to the minus n to the power s, and then multiplicative Haar measure, Tp. What is
Wait,
omega on this?
Why did we know the norm was exactly?
Well, on each of these sets,
Right, on each of those,
this has norm
Right.
1, it's a unit, and then there's a p to the n. So it has norm exactly p to the minus n, p-adic norm.
Right.
What do we know about the character? It's unramified.
I mean, you can say exactly. If it's unramified, it's just what was it? Omega
Yes.
of p to the n or something.
It's exactly right. It was chi. So if it's unramified, it's chi. For anytime you have a unit times some power of p, it's chi of p to that power. So there's this local character chi. So it's, but that character, we can take a single Dirichlet character, mod capital N, of little p to the power n.
Right.
And what's the Haar measure? So now I have a constant. So I have a sum over n. I have chi of p to the n over p to the s to the n times a multiplicative Haar measure of Zp cross d cross Tp.
Mm.
It's multiplicative, so dilating does nothing, and the integral over Zp cross is
1.
1. So this whole thing is 1.
So you literally just get the L function back.
I literally get the p, yes, I'll get 1 over 1 minus chi of p over p to the s, which is the local L function. The local L function for that character at s.
Right. So we're recovering this again, sort of as a Euler product, right?
That's
Because
right.
you're gonna have like this product over all of
Exactly
these
right.
places.
Exactly
Huh.
right.
So I mean, the computation goes through is what you're saying.
The computation goes exactly the same. It's exactly the same computation that we did. We only did a very trivial character here. We could have done a Hecke character. And what we would have gotten, the only L functions we'll see from the GL1 theory are Dirichlet characters. So there's this one-to-one correspondence between these elementary classical Dirichlet characters and the things that we'll get from taking these fancy Hecke characters and doing our Adelic Poisson summation and integral on these.
Somehow we didn't have to deal with like this twisted Poisson. Right?
That's right. instead of having a twisted Poisson summation formula, we take the same theta function. We don't twist here, we twist here. We twist in the Mellon, it's like a twisted Mellon transform, if you like. We can call this a twisted Adelic Mellon transform.
Right. And will we never have to twist the theta function?
Well, more generally, we won't be theta functions, it'll be actual automorphic representations.
Mm.
Well, so Andre, note that we didn't show analytic continuation.
We
did
haven't
was
done
compute-
analytic continuation yet.
All we
That's
did was
right.
compute a local factor,
That's right.
which you don't need Poisson summation for. So if we
That's
wanted to
exactly
get analytic continuation, then we would have to do some kind of Poisson summation.
Yes, and we're going to use
Right.
the known Poisson summation of this theta to do other things with the integral. And we'll
Right, and
replace. So we'll do it next time.
Right. That's what would come next. Okay.
This was all if real part of S was greater than 1.
Right.
So to get the functional equation, we'll need to use not some twisted, but just the Adelic Poisson summation formula, the dilated Adelic Poisson summation.
Yeah.
All right.